Well, hello there, good people. I do have a little bit of a demonstration to show you. So I'm going to start by swiveling this guy around here, and we'll make sure that we are properly aimed. Yes, that is very, very nice. Yeah, okay, we'll go with that. Okay, here I have two cards. This one is named Billy, and this one is named Dan. And Billy has a plunger for a nose. And so if I take Billy and Dan like this, I can squish them together so that now there is a spring that has been compressed through Billy's nose. If I squish them together like this, what is the momentum of the system? Now, before you answer that question, you have to understand what a system is. A system is a collection of objects that we choose to take a look at. So I could say Billy and Dan are the system, or I could say Billy and Dan and the table are the system, or I could say Billy and Dan and the table and the system, and the classroom are the system, or I could say that Billy and Dan and the table and the classroom and the city are all a system. A system is just a collection of items that we choose to take a look at. Now, sorry, I'm going to flip this way just a little bit better. Okay. Now, if I take Billy and Dan and I squish them together like this, what is the momentum of the Billy and Dan system? You would say 0 because they're not moving. Now, here's a question for you. When I let them go, what's the momentum of the system right after I release them? You should say still 0. Today we're talking about conservation of momentum. And we'll find that momentum is conserved anytime you have only internal forces acting on the system. Let's go ahead and I'll pause this video real quick. I'll get resituated and then we'll talk about conservation of momentum. Let me get this figured out. 1 second, team. Okay. We're going to talk today about conservation of momentum, and we're going to start by defining the law of conservation of linear momentum. We say linear here to distinguish from angular momentum, which we haven't yet talked about. Angular momentum is the type of momentum that you have if you go in a circle. You'll remember that we say that momentum is a measure of how hard it is to stop a moving object. It's inertia in motion. And so linear momentum is just a motion moving forward. This is in contrast with angular momentum, which is momentum where you're spinning. It's how hard it is to stop a spinning object that is spinning. So the law of conservation of linear momentum says, in the absence of an external force, the momentum of a given system remains unchanged. Now, there are two terms in this definition that are going to be particularly important to us. First is external force. Whoa, let me try again. First is external, I'm just bad. Okay, first is external force, and the second one is system. We're going to start by defining system. We already started by talking about a system, and then we'll talk about an external force, and then we'll talk about how both of these things apply to the law of conservation of momentum. Let's start by talking about a system. A system is just a collection of objects that we're looking at. Like we said before, it could be Billy and Dan. It could be Billy and Dan in the table. It could be Billy and Dan in the table in the classroom. It could be Billy and Dan in the table in the classroom in the city. It could be Billy and Dan in the table in the classroom and the city and the world. And those would all be totally fine systems. So a system is just a collection of objects that we're looking at. It could be one object. It could be multiple objects. That's what a system is. Now we got to talk about external forces and internal forces. You'll remember that when we had the little law of conservation of energy, the small-time law of conservation of energy, we said that you had to have only conservative forces acting on the system. The law of conservation of energy says that if there are only conservative forces acting on the system, then energy is conserved. Well, the law of conservation of momentum says that if only internal forces are acting on the system. Can you remind yourself before we move on, what's the difference between a conservative force and a non-conservative force? Today we're going to talk about the difference between an internal force and an external force. An internal force, wait, let me get out my pen. An internal force is a force that happens between the objects within the system. It's a force between objects in the system. An external force is a force that is applied to the system from outside the system. You need an external force in order to create a change in momentum. Internal forces will not change the momentum of a system. Let me give you an example. My brother went to Devlin Junior Senior High and had a great time while he was here. But I'm not totally sure like what kind of person he was, like what his character was like. But now he's really he really is one of those fantastic kinds of people who is just always looking to be helpful and always looking for how he can serve other people. And so my brother lives in California, and the other day he was driving down the road when he looked out his car window and he saw that there was a rather old couple on the side of the road with a car that was not moving. And they had it just pulled over to the side, and they looked a little befuzzled, like they needed a little bit of assistance. And so my brother, being the kind of person that he is, he pulled over his car and he got out of his car and he said, "Hey guys, can I be of service to you today? How can I help you?" And they said, "Yeah, we just need to push our car to that gas station over there." And my brother said, "Well, no problem." Now, if my brother said, "Well, no problem," and he went over and he said, "May I?" and he opened the driver's side door, and then he sat inside the driver's seat, and then he said, "I'll push this car to the gas station, no problem," and he took his hands and he put them on the dashboard and he pushed on the dashboard as hard as he could, would that get the car to the gas station? No, because we say that's an internal force. That would be a force inside of the car system, and it wouldn't change the momentum of the car. If the car is still and you want to change the momentum of the car, you need an external force. My brother would have to get out of the car, walk around to the back of the car, and push on the back of the car, applying an external force to the system, a force that does not come from within the system, but a force that comes from outside the system. And that would cause the momentum of the car to change. That would cause the car to accelerate. Hey, do you see how this sounds a lot like Newton's first law? And it seems that all of physics is kind of just right now re-explaining the same things that we already know, but in different terms. Newton's first law says that an object in motion will stay in motion, an object at rest will stay at rest, unless there's an outside force or an external force. So, in order for momentum to be conserved, you have to have no external forces. As long as the forces are within the system, momentum will be conserved, but a force from outside of the system will cause the objects within the system to accelerate. That's the idea of an external force versus an internal force. Now, let's talk about how external and internal forces apply to our Billy and Dan situation. When we started this lesson, I showed you two carts, but I feel like we should change the color because the carts are not the same color as momentum. Okay, let's go with, the carts are kind of brown. Okay, so we had two carts. We had Billy on one side here. Billy has a cool plunger nose. Good for Billy. And then we have Dan over here. Now, if our system is defined as Billy and Dan, here is Billy, here is Dan. If our system is defined as Billy and Dan, and there is a plunger between them. When you squish them together, you squish together a little spring, and so now it's like there's a little spring between Billy and Dan. When it pushes them apart, that spring is an internal force. It's a force between the objects that are in the system. It's a force between Billy and Dan. And so, because it's an internal force, momentum will be conserved. They both start with no momentum. And then at the end, I'll tell you that the system of Billy and Dan has no momentum. But you say, Miss Wilson, that's not possible. Because you started with no momentum. The initial momentum for Billy was 0. And you started with no momentum for Dan. So it's very clear that at the beginning, we have no momentum for our Billy-Dan system. But at the end, you have Dan going zipping back this way, Billy going zipping back this way. Oh, well, you can't really see the arrow there, but that's okay. Arrow. Billy going zipping back this way. You have these two cars both with some momentum. So the final momentum of Dan is something. And the final momentum of Billy is also something. But here's the issue, folks. We're not looking at the momentum of Billy or the momentum of Dan. We're looking at the momentum of the system. Check it out. Suppose that this way is the positive direction. That would mean that Dan ends up with some positive final momentum, and that Billy ends up with some negative final momentum. What happens at the end is that the momentum of Dan is something like, I don't know, let's make it up, 3 kilograms meters per second in the positive direction. Meanwhile, the momentum of Billy is also 3 kilograms meters per second, but in the negative direction. And so if we're looking at the momentum of the system, we can add together the momentum of Dan and the momentum of Billy. And when we add together the momentum of Dan and the momentum of Billy, we get negative 3 kilograms meters per second plus positive 3 kilograms meters per second, and the total momentum of the system is 0. So we say that if Billy and Dan together start with none momentum, then at the end, Billy and Dan, as long as there are only internal forces, at the end, Billy and Dan will end with none momentum between the two of them. And their momentums will cancel out so that the total momentum of the system is 0. Now this is true because there's only an internal force acting on the system. If I decided, though, to take my hand and to put my hand, this is a hand, obviously. If I decided to put my hand in front of Dan as Dan was moving, well, then my hand will act as an external force. I tried to color in my hand. That was a terrible idea. Pretend I didn't do that. My hand's just going to be transparent. Pretend that I put my hand in front of Dan. Well, now that is a force that is external to the system. It's not a force between Billy and Dan. It's a force on just Dan. So if I apply a force on just Dan, well, then I could keep Dan from moving, so Dan's final momentum would be 0. Billy would still have a momentum of negative 3 kilograms meters per second, and so the momentum of the system would change if there's an external force, because they started at 0 and the system ended with negative 3. But notice I had to have an external force to make that happen. Without an external force, if all the forces are just between the objects within the system, then the momentum will be conserved within the system. I'm going to delete my hand because it's honestly kind of scary. Okay. Now, we can also change how we define the system. Let's say that instead of saying that the system is Billy and Dan, I say that the system is just Dan. If the system is just Dan, well, Dan starts with an initial velocity of 0 and hence an initial momentum of 0. But then Billy puts a spring force from his plunger nose on Dan. And so then Dan goes flying, and Dan's final momentum is positive 3 kilograms meters per second. In this case, if the system is only Dan, then Billy's plunger nose acts as an external force on Dan. And if that's an external force, then the momentum of the system is not conserved. So you can see that whether or not momentum is conserved really depends on how you define your system, and also based on how you define your system, whether there are only internal forces or external forces that are acting on that system. Let's look at another example. That's a very bad world. Let's try again. How did the world just stop? Okay, let's do this. Okay, that's not terrible, but it's not the best. Okay, there is the world. That is the planet Earth. And here is a rock. That's on the planet Earth. Now suppose that I take this rock and I hold it up a certain distance away from the Earth. If I'm holding the rock a certain distance away from the Earth, well then, right now, we would say that the momentum of the rock-Earth system is 0. Wait, let's change our color here. Ooh. I almost sneezed. It might still happen. It's a potential possibility, just giving you a forewarning. Okay. The momentum of the rock and Earth system right now is 0. Now, if I let this rock go, this little rock will start accelerating down towards the Earth like this. And so, the rock will now have some final momentum. Ooh, I forgot to say initial. Boop. The rock will have some final momentum that if we say, let's call down the positive direction, let's say that it ends with a final momentum of positive, let's choose a number, 2 kilograms meters per second. Now, meanwhile, the Earth will also start accelerating up towards the rock. And the Earth will start accelerating towards the rock so that the Earth has a final momentum as it's heading towards the rock of negative 2 kilograms meters per second. Notice, between the rock and the Earth, there was only an internal force. It was a force between the objects in the system, and it was a force that we call the force of gravity. So gravity was enacted here as an internal force pulling them both towards each other. Because it was an internal force, we say that the total momentum of the system is conserved. So we started with none momentum and we end with none momentum because we have the rock has a positive momentum and the Earth has a negative momentum. Now check it out. They both have the same momentum going in opposite directions, but the mass of the rock is tiny, so the velocity of the rock is big. Meanwhile, the Earth has an enormous mass, so it has a very, very tiny velocity pulling it back up towards the Earth, or pulling it back up towards the rock. So momentum is still conserved here, but you can see that the masses and velocities are different sizes, so what the momentum looks like for both the rock and the Earth looks totally different. Can you explain how momentum is conserved if you jump off a table? And now we're going to go ahead and look at a little practice problem. Suppose that you, let's suppose that this situation happens to you. Suppose that all of your friends throw you out onto a frictionless lake and say, have fun finding your way back, because they think it's funny, like a prank or something. And so then they leave you on the frictionless lake. Well, yes, you probably need new friends, but they leave you out on the frictionless lake with nothing but the clothes on your back. You are stuck on a frictionless lake with no way to get back except that you happen to have boots on your feet. Suppose that you decided that if only you could throw your boot this way so that your boat starts, so that your boot starts moving away from you this way, then you would say that would then cause me to move back this way. And you know that that's true because you say momentum is conserved. If initially the boot and I both start with no momentum, then at the end, if I give the boot some momentum, my momentum will have to cancel out with the boot's momentum, because when I throw the boot, there's only an internal force between me and the boot. It's a force that goes between us. It's between the objects in the system. Could you figure out how fast you would have to throw the boot in order to launch yourself backwards? Suppose that your mass, that's the mass of you, is 60 kilograms. Suppose that the boot, has a mass of 1.0 kilogram. And suppose that you would like to start heading back towards the shore with a speed of 0.50 meters per second. The question is, let's move this guy up. Okay, come on, you can do it. The question is, how fast will you have to throw your boot? Now, when we try to do one of these kinds of problems, the first thing that we do is we do always draw an initial picture and a final picture. We're showing what the momentum looks like at the beginning and what the momentum looks like at the end. The next thing that we have to do, because momentum is a vector and it does have direction, is we do need to define our axes. So I'm going to say that the direction that I throw the boot is the positive direction, which means you are going to end up going in the negative direction, and you do need a negative sign there. The next thing that we do is we say, because only internal forces happened to act on the system, the change in momentum of the system is going to be 0. Or in other words, the amount of momentum that you start with in your system is going to be the amount of momentum that you end with in your system. The amount of momentum that we started with in this system was 0 because nobody was moving here. We started with none momentum. And then the amount of momentum that we end with here is going to be your momentum plus the boot's momentum. So that's going to be the mass of you times your final velocity. Oh, whoa, gosh, help! I accidentally drew a vector hat on my M. Okay, whew, that was a close call. Did you guys see that? That got really dangerous here. Oh my gosh. Okay, plus the final momentum of the boot, which will do mass of the boot times the final velocity of the boot. Okay, now we rearrange to solve for what we're looking for. We are looking for the final velocity of the boot, so we'll move this on over to the other side, and we get negative the mass of you times your final velocity. That's going to equal the final velocity of the boot that you need to throw it with, divided by the mass of the boot to get it all on one side. When we plug in numbers here, we find that the final velocity of the boot is going to equal negative the mass of you, which is 60 kilograms, times your final velocity. You want to end going with a speed of, or a velocity, of negative 0.50 meters per second. We do plug in signs here, and that's going to get super, super critical that you plug in signs here. All divided by the mass of the boot, which is 1.0 kilogram. You could probably do this in your head. You would get that you need to throw the boot with a velocity. When you throw it, it needs to end with a final velocity of 30 meters per second. Check it. This negative sign cancels with this negative sign, and we get in the positive direction, which is exactly what we expected. So you only need to throw this guy about 65 miles an hour. And that's how we do a conservation of momentum problem. I have one more problem for us to do together. Let me go ahead and pause this, and I have to grab my textbook really quick. Be right back. Hello, good people. So I did get my textbook, but on second thought, I think I'm going to wait to do this question until our next video because it goes much better with the content that we're going to be doing in the next one. So I will add it to the next one. For today, we talked about conservation of momentum. We started with the law of conservation of momentum. We talked about what a system is, what an internal force is, and then we talked about a few different situations where the initial momentum was 0, and then we found that the final momentum was also 0 when you account for direction. And that's all for today, folks. I hope you have a wonderful rest of your day. Bye, good people.